Hi everyone, I am Yi from University of Science and Technology of China. We are going to talk about our latest work, TLP, a deep learning-based class module for tensor program tuning. A tensor compiler generally consists of three parts: the front end, the back end, and the middle end. The front end is responsible for transforming the workloads of each deep learning framework into a unified representation. The back end is mainly accountable for hardware-related code generation and optimization. The middle end generally includes two intermediate representation layers for transforming and optimizing the graph and tensor layers. TLP is used to guide the generation of high-performance tensor programs from computational subgraphs. We take a fused dense plus ReLU activation as an example. On the left, the mathematical expression directs a cyclic graph. A naive tensor program are different representations of computational subgraph and are computationally equivalent. Different tensor programs will be produced when different scheduled primitive sensors are applied. These tensor programs are also computationally equivalent but have different execution latencies. Instead of extracting features directly on tensor programs, TLP extracts features on primitive sequences. To our knowledge, TLP is the first class module for tensor programs that extract features directly from the scheduled primitive. Tensor program tuning is about finding the highest performing tensor program from a search space of millions, even billions. The most accurate approach is that execute each candidate on the target hardware, but inefficient. Most compilers resort to the algorithm guided by cost model. However, in building a powerful cost model, previous works fall short in some aspects. The primary hurdle to overcome is feature extraction. With previous approaches such as Answer and Tiramisu relying on complex feature engineering and constrained by prior knowledge, while adopting a deep learning-based cost model can yield significant performance benefits. It introduces a secondary challenge: lack of hardware portability, a problem we call cross-hardware unavailability. A cost model developed on hardware A may experience a drastic drop in performance on hardware B. Currently, there are limited studies on addressing cross-hardware unavailability. While Tensor employs transfer learning to tackle this challenge, its performance remains suboptimal. On the other hand, Moses employs a model distillation as a solution, but is not available as an open source. This image provides TLP's system overview. During training, TLP extracts features from scheduled primitives and leverages the measured programs as labels to train the cost module. During inference, TLP predicts the cost of different primitive sequences and selects k-sequences with the lowest predicted cost of potential candidates for generating tensor programs. First and foremost, our objective is to predict the latency of tensor programs. TLP accomplishes this by regarding scheduled primitive sequences as the equivalent representation of tensor programs. This raises two crucial questions. Why are scheduled primitives a suitable proxy for tensor programs, and how does TLP accomplish this task? To begin with, let us answer the second question. How does TLP extract features from scheduled primitives? We break down a primitive into three components: primitive type, numeric parameters, and character parameters. The primitive type is transformed into one hot vector, numeric parameters remain unchanged, and character parameters are tokenized, following a similar approach as in NLP. This is the specification of extended Backus-Naur form. A primitive sequence is composed of three primitives, where each primitive begins with a primitive type and is followed by numeric and character parameters. The TLP extractor processes these three parts into primitive independently. F1, F2, and F3 can be treated as interfaces, and their implementations can be substituted with other good solutions. Here's the pipeline of TLP. It begins by removing unnecessary parts and then converts the remaining pieces into numeric vectors. This process is reversible, which is fundamentally different from methods based on statistical features such as answer, which are irreversible. The resulting numeric vector is then fed into the neural network to obtain the predicted value. Next, answer the question of why. This again breaks down into two sub-questions. First, why can a primitive sequence be considered the equivalent of a tensor program? The answer is that they almost have a one-to-one correspondence, containing the same amount of semantic information. In the case of Tensor CPU dataset, there are 8.56 million different primitive sequences in 8.65 million tensor programs, with a repetition rate of only 1.043%. If a scheduled primitive sequence has two labels, the cost module does not converge. The second sub-question is, why do we extract features from scheduled primitives? There are mainly several advantages. First, these features are dense and preserve all information considerably. Second, the primitive sequence is a regular sequence that can take advantage of existing NLP techniques. And finally, we do not need complex feature engineering. By the way, we call scheduling primitive the tensor language. TLP is thus a tensor language processing task. To address the issue of cross-hardware unavailability, we utilize multitask learning. Specifically, we split the TLP network into a backbone and head. We leverage the head to learn the domain gap between different hardware. However, since the target hardware has a minimal amount of data, no label might be available to a given piece of data. In such cases, we do not compute the loss of the target hardware or update the head parameters related to the target hardware. MTL-TLP plays a significant role primarily due to the following reasons. Firstly, MTL effectively increases the sample size. Secondly, in single-task learning, the backpropagation of gradients tends to get stuck in local minima. MTL acts like a regularizer by introducing an inductive bias. Lastly, MTL-TLP can be shared parameters to fit hardware-independent features and non-shared parameters to fit hardware-dependent features. Finally, the evaluation part comes. We will evaluate TLP and MTL-TLP from both dataset-based metrics, and search can provide a broader evaluation on multiple hardware datasets, while search-based metrics allow for deeper and more accurate assessments. For the dataset-based metrics, we will use top K criterion for evaluation. Specifically, for a given subgraph, the top K score is defined as the ratio of minimum latency of all samples to the minimum latency of the K samples predicted by the cost module. For test set, the top K score is weighted average of all subgraphs. This table compares TLP and Tensor MLP on experimental hardware platforms consisting of 5 CPUs and 2 GPUs. TLP outperforms Tensor MLP by a large margin on CPUs, while on GPUs, both models each have their strengths. This can be attributed to the feature extraction approach of TLP, which just encodes all features and delegates the weighting of their importance to the neural network, rather than manual pruning features. Next, we verify the effectiveness of MTL-TLP. We specify E52673 as the target platform on the CPU and set 1 to 4 heads. Respectively, the target platform only uses 500,000 pieces of data, which accounts for just 7% of all data, while the other platforms use all data. GPU experiments are similar. The following observations can be made. First, multitask learning can significantly improve accuracy. Second, even with only 500K data, MTL-TLP outperforms Tensor MLP. Third, appropriately increasing the number of tasks can further improve the accuracy of cost module. The following are end-to-end tuning experiments. The CPU experiment was conducted on a notebook equipped with an 8-core Intel i7, while the GPU experiment was conducted on an NVIDIA Tesla T4. The graph represents the time it takes for TLP and Tensor MLP to perform 2,000 tunings. On average, TLP is 1.7 times and 1.8 times faster than Tensor MLP on the CPU and GPU. Respectively, this is because TLP directly extracts features from the scheduled primitives without generating tensor programs, saving significant tuning time. Here are the tuning curves for 5 workloads on CPU and GPU. The horizontal axis represents search time, while the vertical axis represents inference latency. These curves demonstrate that TLP and MTL-TLP can converge to lower values faster. These two graphs depict the search time required to achieve the performance of answer and Tensor MLP tuning 2000 times. The results indicate that TLP/MTL-TLP can significantly reduce search time. To sum up, we make the following 3 contributions: a simple yet efficient and general feature extraction mechanism for tensor programs, a multitask learning method to address across hardware unavailability, a solid implementation, and comprehensive evaluation. Thank you for listening.